So when we're talking about taking notes, we're talking about organizing your work and on your paper, but also that organization, what it does is it improves your ability to process the information long term. So one of the things that helps you organize your notes is to make sure you label the notes. So what exactly it is that you are what you're writing about on that page. So in this case, it would be atmospheric composition and lab 1, because that's your first lab. So now if I were trying to review for a final, I know that I'll have to just flip through my notebook, and when I see atmospheric composition, lab 1, I know where that information was discussed. Also, you want to put your header on things. So in this case, it would be your name, and I left a blank space on the version that I gave you, and that's one thing you had to fill in. I put the date. In this case, it was August 6th, 2019, and your class, which of course is Honors Biology and or AP Environmental Science, whichever it was, and period. And the period, of course, is dependent on what period I have you. You were supposed to fill in the blanks. Now, over here, on the left-hand side of these notes, this little wiggly line that I drew, and you see how quickly I drew it. You don't have to pull out a ruler and do all kinds of crazy things. But on the left-hand side of the first wiggly line, you can put a keyword, or maybe you put a question. So here you see air, that's a keyword, and now those are examples of reflection. Also, I am reducing the information. Reducing what information? The information that I'm going to write here in the main portion of the writing, of the notes, of the recording. And the notes are known as recording. So I'm recording the information. Now, when you do a summary, that's here at the bottom, you're doing a summary. Again, you are both reflecting and you are reducing. To reduce requires reflection. All right, so you're reflecting and you're reducing the information that you have on the details here into something more condensed. So that being said, your notebook will look something like this. One of the things that I wrote down air is made of blank, is what I had put. It is a blank of blank, period. You were supposed to fill in air is, and I wrote this on the board and I discussed it out loud. Air is made of gases. It is a mixture or solution of gases. And that's all you had to write down. Now I had put the information on the board and you were supposed to fill in, and I said it out loud, and you're supposed to fill in what was missing. The next paragraph in what I had given you, what you should have in your notebook, is gas is a blank with covalent bonds that do not stick together very well. In fact, they push away. And create pressure. Now, gas is a blank. It's a group of molecules with covalent bonds that do not stick together very well. They push away and create pressure. And the example that I gave you in class was that of a balloon, and I showed you the gas on the inside was pushing outward in every direction, creating this three-dimensional shape. But there was gas also on pressure from the outside gas pushing in from every direction. That was going to be important later on in the conversation. And that gas on the outside, we said that was air, right? Then as we move forward, we said that there was this blank pressure pushing in, would blank the balloon if there was not blank outside to balance it out. So some pressure was pushing in, would blank the balloon if there was not pressure or something outside to balance it out. I shouldn't have put outside, I should put inside here. All right. So what kind of pressure what is the pressure that's pushing in? Well, it's air pressure. Air pressure pushing in. Let me write it in red so you see air pressure pushing in would collapse the balloon or shrink the balloon. Let's put shrink. If there was not air pressure inside to balance it out. So the air pressure on the outside would collapse, make the balloon get smaller if there wasn't air inside pushing out. The idea seems straightforward enough, and you can think of a tire on a car as a good example, or a balloon in this case, and you can imagine that the pressure inside and the pressure outside would balance each other out, then it'd be a stable balloon. And one of the questions I asked in class is what would happen if you took some of this gas away? Well, you'd imagine you'd have less air pressure, so the balloon would get smaller, right? So what would be a good summary for this slide? Well, you could write whatever you feel is important out of this, but what I would say is something like air is made of gases, that create pressure on the containers from or in all directions. So that would be one good summary. I think what I wrote was air is made of gases. Gas is a set of molecules that don't stick together very well, and it creates pressure. That would have been the blanks that you would have to fill in that chart, in the copy of the notes if you were trying to do that. So that's what your notes would look like in a notebook. Now, a suggestion, don't have to do it, but I like numbering my pages. So if you can have a notebook and cut number 1, so page 1, maybe you don't want to number the first page, that's fine too. When you're going back and you're changing things or adding things, what you would do is that would be called revision, right? So that's revising. So when you're revising the notes, you're adding to the notes, and or you're subtracting or you're correcting the notes, and by doing that, you end up creating something that is that's powerful. You end up working out when you're revising, when you're reflecting, when you're reducing, you're improving your thinking. You're thinking about these things. And if you think about these things, then you end up improving what you do. You improve your understanding. So that being said, the other thing you can do is you can take an index card and you can cover up the main idea. You just ask yourself, well, what is this? This is air. Or you can cover up, maybe you want to cover up the details. And by covering up the details, you can ask yourself, what is air? Air is this. Maybe you write down air pressure. Air pressure. And if you write down air pressure, or you go ahead and you ask yourself that question: what is air pressure? And if you know the answer, you can check. Air pressure is this. Well, there it is. It's true. That's what air pressure is. It's the pushing of the gas. Now, you could also write questions over here. One of the questions that I wrote was, why does... Hello. I'm pausing now. There's someone just came in. So one of the questions, as I was saying earlier, is why does the straw with a thumb over the top not drop the water? Now, there's a good question to ask. Maybe we should just ask it in the next page. But you can ask these questions and put them on the side. Maybe you're to be more. Oh man.
Staff and families at this time, our back to school meet and greet has ended.
So when we looked at our experimental setup, we look at the beaker that we had, and the beaker had some water in it, and there was a test tube that was inverted, and at the top of the test tube was some steel wool, and steel wool had iron and carbon. It's an alloy of iron and carbon. Iron is one of these elements, and Fe is the symbol for iron. Now, the iron will become important in a minute. Now, consider that there's air pressure pushing down on the water, so that in all directions. And since this is a glass container or plastic containers, the air pressure that's pushing down on the surface of the water is what's important here. So, of course, the water is going to get pushed down, and it's going to flow into the test tube, and it's going to flow to the point until the air that's inside the test tube resists the water coming up. Now, because both the pressures were equal in the beginning, and the air is pushing on the sides of the container as well, but that doesn't really impact the water level, right? The part that impacts the water level is the pressure that's pushing down. So inside the test tube, you see, the pressure in the test tube is equal to the pressure from outside the test tube, and we know that because the water level is the same. I hope that makes sense to you. All right, so when we add the iron, so we know at this point that all the water pressure is the same. Now the question is that we asked is, what would happen if we got rid of some of the gas that is inside this test tube? What would we expect to happen to the water inside the test tube? Right? So we have to think about the idea that gas is creating this pressure, that the gas is constantly pushing down in all the sides, because that's what gases do. They expand and they put pressure on the surrounding area. So they expand until they hit a side of a container, and they're going to keep pushing on that, just like the balloon, right? So if we got rid of some of the gas inside this chamber, what would you expect to happen? What do you think would happen? Well, I hope you're saying to yourself, well, I'd expect to see less pressure pushing down on the inside. So if outside the atmospheric pressure is pushing down at 1 atmosphere, and inside you're pushing less because you got rid of the oxygen, then you'd expect the water level inside the test tube to go up over time as the oxygen gets removed. So I guess the next question then, and you'll see that the next drawing in the notes is another one of these beakers with a test tube, and the iron's in there, and you have the water level, and you'd expect the water level to be higher over time than the surface water level of the test tube, because the pressure is still pushing down at the same rate on the outside, because you haven't changed the air pressure outside, but you decrease the amount of gas here because you reduce the oxygen. We said if we got rid of the oxygen gas, right? If we remove some of the gas, in this case the oxygen gas, we'd expect that this pressure would be less. Notice the arrows are smaller. And since there's less pressure, the water's going to move up. Well, that makes sense, right? But the question we had in class is then, how do we then remove the oxygen from inside the test tube? That brings us to the iron. What we said was that iron reacts with oxygen. Iron reacts with oxygen in the air to make rust. And so you get iron. Remember, that's Fe. That's the symbol Fe. And it turns out it's iron plus 3. So that's iron. Iron solid, S for solid. It's usually black and or some kind of dark metallic color. And it's hard. All right, and it's solid at room temperature. And if you add to it, if you add to the iron some oxygen gas, what it forms is this thing called iron oxide, and it's FeO3 really. It's red. It's flaky. It's actually soluble in water. It'll dissolve in water where the iron does not dissolve in water. The iron oxide does. So it's a solid, but it dissolves in water easily. It's water soluble. And it's brittle. It falls apart very easily, where iron is harder. Iron oxide is brittle, falls apart. That's why people don't like it on their cars, and that's why you get holes in the car, because the iron oxide falls apart. Again, this is another word. Iron oxide is another word for rust. Now, as an aside, we said, as just an interesting note, we said, remember that this happens in your blood, or at least to some extent. The iron in your blood binds the oxygen that you breathe in, all right, and binds the oxygen in red blood cells. There's kind of a connection to this process. It's not quite rust. It's not quite a full oxidation, but similar enough. So again, you have this iron. In this case, the iron is in these kind of like a wool looking, like almost a fiber, but it's a solid. And let's just put a block and call it iron. And that iron is just going to bind the oxygen gas. It's going to take it from a gas form. The gas, remember what a gas was. We defined it as this at room temperature. They expand really quickly. It's in the molecules fly around, but the iron's binding it, capturing it chemically. And as the iron captures it, it forms rust, and that rust is iron oxide. Or rust. So that rusty red color, what that's telling you is that the oxygen's left the air. It's no longer in that space, right? And it's formed a solid. So it used to fill up that space, and now it's bound to, and dense, and it's in a solid form. So the oxygen gas, the oxygen used to be a gas. There's, for every one iron, 3 oxygen atoms get removed from the air. So the solid iron is going to, as the iron rusts, the solid iron takes 3 oxygen atoms for every 1 iron atom. And what you get is a solid iron oxide. So we called this a chemical reaction. So this is a chemical reaction because we did not destroy the oxygen, right? We removed it from the chamber. So remember that the chamber was that test tube. Right. The iron that's at the top here is removing the oxygen. The oxygen, so these little red dots, and they're going and binding to the iron. And because they're binding the iron and forming the solid, they're not pushing against the water anymore. So they stop pushing against that water. So less and less of the gas is there as time goes on to push against the water, and the water line here keeps moving up as there's less and less gas pushing down. Well, where's that gas going? Well, it's not disappearing. The gas is reacting and turning into iron oxide, it's turning into rust. All right, so so you could add questions to the side. It's kind of a reflection idea. What is rust? It's a combination of iron and oxygen, right? Iron making iron oxide. There's you can ask, what is a chemical change? Or a chemical reaction. Right? What is a chemical reaction or chemical change? When we say it's a chemical reaction, what do we mean by that? Well, to be fair, what we're saying is that instead of these two oxygens, because that 2 means there's 2 of these atoms that are oxygen, we got the oxygens are leaving each other and then binding with the iron. If you drew it out as a shape, you'd have oxygen bonded to oxygen here, and you're adding it to, as a ball and stick model, you're adding it to this iron atom. And if you're going to balance it, you'd need you need 6 of these oxygen atoms or molecules, and you'd need 2 of these iron atoms. And if you combine these together, what you'd form, because remember we said 1 iron atom and 3 oxygen atoms, what you'd end up with is an oxygen atom, an iron atom here, the black one, with 1, 2, 3 oxygen atoms each, and we call these iron oxide. And you started with this iron solid and this oxygen gas, and you end up with rust. And rust is a solid at room temperature. So that's what's going on chemically, and we'll learn more about this next week. So this is just trying to give you some deep understanding about what's going on in this chamber that allows for the gas to go away. The key here is that you start to get an inkling, an idea of what a chemical reaction is, but the main idea of the lab is that we're removing oxygen here, and the percent of oxygen that is removed, if we assume it's all completely removed, then this line, whatever percentage it is that it goes up, is the percent oxygen inside air. Because remember, that's the whole point of the lab. We're trying to answer that question: what is the composition of air? What percentage of the air is oxygen, and what percentage of the air is nitrogen, and what percentage of the air is some other component? So we're answering with this experiment what percentage of the air is oxygen. If it goes up 50%, then about 50%, then we lost 50% of the gas. So that means 50% of the air is oxygen. If it goes up 20%, then 20% is oxygen, etc. This whole diagram here is just explaining how we remove the oxygen. That the iron binds the oxygen, that these gas atoms, these oxygen atoms that are bonded together. So see how this little line represents the bond, the chemical bond between two oxygen atoms. And these iron atoms that are just kind of associated, they're not really bonded together, but they're associated together. They're solids at room temperature. This is a gas at room temperature. That's the gas that's in the air we breathe. When something rusts, when they react, when the oxygen comes into contact with the iron, these atoms of oxygen bond to the iron and you form rust. Now notice you have two solids on this side, you have two irons on this side, you have two on this side, two black circles here, two black circles here. You have 6 blue circles or 6 oxygen atoms here. Notice you have 1, 2, 3, 4, 5, 6 on this side. This is called a balanced chemical reaction. Again, we'll talk more about this later. I'm not too worried about you learning a balanced chemical reaction. You should learn that in physical science. You'll certainly learn that in chemistry. But the key here is that this chemical reaction is what removes the oxygen from the inside of this test tube. And by removing that oxygen from the inside of the test tube, you get the water level moving from here upwards. Let's go ahead and see what the next page of your note says. So the next page of your note says, okay, well, we have the drawing. We looked at all that. We know that there's iron up here. We know that we're putting it in water. We know we soaked the steel wool with a little vinegar and water to make sure that it rusts quickly, that it helps the rust, and we said that was very much like salt on the roads. It increases the rate at which that reaction happens. And we said that steel wool, and we said that steel wool is iron mixed with carbon, but we were really worried about the iron. All right, I hope you remember all that. We just went through it. So now the question then is, what's your hypothesis? What's your guess of what's going to happen when you put that, now that you knew all that you knew, and I kind of gave it away already because I explained it, what would you expect to happen to this water level inside the test tube as time went on with the chemical reaction? And what it says in the notes is what is going to happen when the steel wool soaked with water and vinegar sits in the test tube over time. What would you expect as results? So what is going to happen? What do you expect is going to happen? So one would expect to say that the hypothesis then is if the iron reacts with the oxygen gas in the test tube, and that gas no longer resists the pressure from the atmosphere. Then one would say then the water level will go up in the test tube. As the iron reacts. And, you know, I pretty much explained why all that happens, and this is your hypothesis. This is a scientific guess based on the knowledge that you know. You expect this water level to go from here up to some point, and you expect that change. I'm going to put this triangle. It's a Greek letter delta. This delta, this triangle, that change to equal the change should equal the percent oxygen gas of the atmosphere. That's what you're expecting here. So, you know, that's, again, what are we looking at when it comes to notes? So there's kind of three key points here. Point number one is that you're dealing with how do you take notes. Point number two, that you're dealing with some chemical reactions here. You're looking at the iron reacting with the oxygen and removing it inside. Point number three, and maybe you should write all these down for you. So when we're looking at this, what are some of the takeaways here? What are the key points? Let's say testable points here. Point one, that iron reacts with oxygen, and that reaction takes oxygen out of the air. That's a key point. If you're going to try to explain your conclusion, if you're going to make a conclusion based on your experiment, you have to have that in mind. Keep that in mind. Part two here, and kind of explain some of your experimental design, is that the acid helped, and the acid in this case is vinegar, helped the iron rust, the iron oxygen reaction. All right. Number three is that gases induce pressure. And they induce pressure by the more gas, the higher the pressure. So again, the more gas, the higher the pressure. So therefore, so let's look at it again. Iron reacts with oxygen, and takes oxygen out of the air. That's point one. The acid helped the oxygen-iron reaction. Gases induce pressure. All right. So if you have gases so the more gas you have, the higher the pressure. And we talked about that. We talked about the atmosphere. We talked about the thicker the atmosphere, the more pressure there was. We discussed that. So those three statements, it's getting late. If those three statements are true, then you have to say, if those three statements are true, then, right? This in geometry, this is used to say, in a geometric proof, this would be therefore. If this is true, then it follows that the next portion is true. if it's true, if those three are true, the more gas you have, the higher the pressure, and iron takes oxygen out of the air, then over time there should be less pressure in the tube. Comma, where the reaction is happening. So let's be clear. I'll draw this out one more time. You have this there's this water. It separates the chemical, where the chemical reaction is happening, which is here inside the test tube. Here's the iron inside the test tube. Here's the water that's separating, the water's all inside the test tube and out. Here's the pressure outside the test tube. It's pushing down. That pressure is equal to 1 atmosphere. We talked about what that pressure is, 1 atmosphere, because that's the pressure from a column of air going from sea level all the way up to space. All that weight of that gas, of the air pushing down, is pushing down on the surface of the water. And that's constant. That's not going to change. The only thing that's going to change that is if a storm front comes through, right? A low pressure system or a high pressure system, just like they tell you in the weather on the Weather Channel. That's really the only thing that's going to change. Or you move to the top of Mount Everest or the bottom of Death Valley. That could change the pressure, but in general, it's not. In nature, here in Cleveland, the air pressure is going to be generally the same from 1 minute to the next. So the air pressure is pushing down constantly. For all intents and purposes, it's constant. But inside this vessel, as you see, as we just discussed earlier in the previous previous discussion here, inside this test tube, the iron that's soaked with acid that's inside the test tube is binding the oxygen, taking the oxygen out of the air. So less and less of this gas is present to push down. So then there should be less pressure in the tube as the reaction keeps happening. And the less pressure you have, the higher this water should go, right? This water should be moving upwards until all the oxygen's gone. Once all the oxygen's gone, this iron's not going to rust anymore. So as soon as this water level is going to stop going up. So if this movement is 20%, if it moved up 20% from where it was, if from here to here is 100%, right? And the water level moved up, I don't know, I'm going to guess it's going to be something like this, something around here, and we say that's 20%. So then we can say that, and it doesn't go up any further. That's it. That's as far as it moved. Then we can make a good guess that about 20% of the, I'm going to put this little symbol here, about 20% of the atmosphere is oxygen. It's a beautiful lab. It's a beautiful, logical lab. Now notice that it depends on a few things. It depends on a lot of things. It depends that this chamber is separated from the outside, so you can't have oxygen, can't have exchange. This has to be a closed system. We call it a closed system. In other words, there can't be exchange of gases from inside to outside. Can have a hole in it, for instance. It depends that the air pressure outside, the atmospheric pressure, is constant. And we know, as I said a moment ago, that the air pressure does change from moment to moment, but it's relatively constant. All right, relatively constant. It's not going to change too much from point from one day to the next in the laboratory. And we know that the gas is being removed slowly as the oxygen reacts with the iron and turns to rust. So we know these things. We depend on these three things being true, and that if there's less gas in here, there's less pressure. If that's true, then the water level should go up over time, and indeed we see that. If we take a look at an actual experiment here that was done, is beautifully conducted. They followed all the rules, and they said the original line for the water level was here. Let me make this a heavier line. This was where the line was. As you can see, the water line is still pretty much there. Let me actually make that a little thinner. Here's the line here. You know what? Here's the line, right? The water line. Still, I don't like it. Let me make it blue. Ugh. Here's the line. And this is where the water line is now. So you can see that there's a movement of water inside the test tube, not outside. Outside the test tube, you'll notice that there's nothing here. There's no water here. There's no water here. No water out here. But the water did go from there, where the surface of the water is touching here, this water, inside the test tube, it went up. So that's really interesting. Water out here went down a little bit. Water inside the test tube went up. That makes sense as air pressure is constantly pushing up. Some of the water is going to go up into the test tube as air pressure pushes up, as this iron rusts and takes the oxygen out of the air inside the test tube. All right. So this is an example, one of the experiments that worked out really well. And that's how you would explain it. And what we're going to do is, over the weekend, we're going to take the data. We're going to take some data that we're going to collect on Friday, and we're going to make a chart, and you guys are going to graph it. And you guys are going to come up with a conclusion, and we're going to discuss experimental design. We're going to discuss what a lab report looks like. So we'll look at what an experimental design is, and we'll look at what's the independent variable, what's the dependent variable, what kind of growth, what kind of change was there in the volume over time, what percentage of this of the atmosphere is actually oxygen based on the 100% that is the test tube, and hopefully we'll get that data and we'll make sense of it. And this lab I hope it feels like a success. And if the water didn't move in your test tube, really what we want to do is look at error. You know, what kind of error did we have? Where did we go wrong? Was it an issue with experimental design? Was there a design error? Was there a flaw in the design? I don't know. We can discuss that. Was there a mistake done by a procedural mistake? Did someone shake it, move it, not settle it? Was there too much steel wool, not enough? Did you not dip it in the vinegar? What was the result? All right. I know the video was pretty long, but I think that's what you guys wanted me to make and go through it. Again, we'll finish the experimental design and we'll do safety tomorrow. You guys take your time and read it. And some of you might be asking, well, what is it that I need to know for the quiz? What's the bottom line here? Do I need to know all this? Look, I think that if you understood the procedure and you understand that we remove the oxygen in the test tube by reacting it with iron, I don't think you will not have to understand the chemistry of it. You won't have to balance the chemical reaction, for instance, or you won't have to tell me that there's 3 oxygen atoms for every iron atom. But you would have to understand that the iron in the steel wool is what's reacting with the oxygen, and it's taking the oxygen from gas form to solid form. So from gaseous oxygen to solid iron oxide. I think you need to know that, because that's a fundamental point in the lab, right? I think that's how we're removing the oxygen inside the test tube. I think you have to understand that gases produce pressure, and that pressure, once you remove the pressure, that you see the water moving up the column. I think you need to be able to describe that. And I think you have to be able to describe how to, if I'm asking you, if I give you a paragraph, for instance, and I say, well, what if the oxygen, the water line moved up 5%? What would that say about the the percentage of oxygen inside the test tube, right? So let me give you an example. If I, on the quiz, give you a test tube, and I give you a beaker, and I put that test tube in water, and I say to you, well, after we started with this much water at this point here, that was my water line. After a day or two, the water moved up to here. So I would say the entire test tube had 100 milliliters, held 100 milliliters, and was 100 milliliters of oxygen. But after the experiment, there was only 70 milliliters of gas left. The water moved up that much. Well, so that meant that how much gas then was lost? How much was lost if you had 100 and you ended up with 70? Hope you say like 30 milliliters, right? It's 30 plus 70 is 100. So about 30 milliliters. So what percentage is that? What percentage is 30 milliliters of 100? Well, I gave you 100 on purpose. It seems like a real easy number. So if it's 100, and you ended up with 30, you had 30% of this sample of gas was oxygen. How do you know it was oxygen, not some other gas? Because oxygen is what reacts with iron. Nitrogen does not react with iron, and the other component gases pretty much won't react with iron. There might be a gas in there that might, but there's not a high enough concentration to measure. So it's nitrogen and oxygen, and so oxygen reacts with the iron, and that's what's being taken out of the solution of gas that we call air inside this tube. So you should be able to calculate like what percentage of oxygen is there if I give you a scenario. You should be able, and we're going to go over that a little bit tomorrow, but that seems like it's something that's reasonable if you understand what's going on in the experiment. You should be able to tell me when we're doing on the quiz, what are the components of Cornell notes? Like, what is it that I should be writing down? What are the cues, right? What are the cues that tell me that some information is important? Repeating the ideas in class, telling you it's going to be on the quiz the way I did several questions I told you was going to be on the quiz. What is a gas? That a gas is a molecule of a molecular compound or two atoms bonded together, however you want to say it, is a molecule that is not as sticky as some other molecules, and that at room temperature, because of that, their energy, their kinetic energy, has them moving around in a room, adding pressure to the sides of a container. So they create pressure, so gases create pressure. It's a simple idea that, gases fill the air. They fill the space they're in, whatever that space is. They're moving, they're constantly moving. So that's what a gas is as far as we're concerned at this point. that's pretty much it. I don't think the quiz is going to be that difficult. I think if you paid attention and you followed you followed along with the notes and you've done the lab, I think you should be able to and you've taken your Cornell notes. Remember, you're going to be able to use your Cornell notes on the quiz. Then you should be fine. Don't forget to read the syllabus, as we said yesterday or today. Read the syllabus. Know those 3 questions that I told you I was going to ask on the quiz. Know this stuff that we've discussed here, and understand the experiment that we've been doing. All right. That's it.